Hello everyone, this is James Boyce backing in for RL Education. Today we're going to be talking about what we can do when our variables vary. And so what I mean by this is, for a typical question, you might be looking to find out, for example, the work done on a certain object, and we know that the formula for work is just force times distance. And so if you have a force of 100 and a distance of 10, then all this is going to be is just 100 times 10, which is just 1,000 joules. And that's all you have to do. However, in realistic scenarios, sometimes the exact amount of force being applied to the object will vary throughout its journey. Now, if you can break this down to nice, easy chunks to work with, you can just apply this multiple times. But if you have something more continuous, it becomes a bit harder. So to analyze this, what we're going to do is we're going to look at a graph. For the example we've got here, we've just got a force of 100 times a distance of 10. And if we graph this force against distance, 100 is constant for the entire duration as it's being pushed over a distance of 10 meters. So the graph just looks like this. And then after the 10 meters have gone, the force goes down to 0. And so we can see that the work function we calculate 100 times 10 is going to be exactly the same as the area underneath this graph. We've got this 100, which goes across all the way here, which means the height of this graph is 100. And we've got this 10 here, which is going to then give us the length of this graph. So this is 10 long, 100 high. So the area of this is 100 times 10, which is exactly the same as the work function we just found. So we can see that there's an analog between multiplying two variables together when they're constant and finding the area under a graph of those two variables. Luckily for us, even if the graph is something more ugly like what I've just drawn here, we can still apply this same analog of the multiplication of variables being the same thing as the area under the graph. So if we look at the situation we've got here, we see that we can break the early part of this graph here down into nice discrete parts that could all be handled quite simply. For example, this one here, constant force, constant distance. If we times those two out, we can find out the work done over that section. Similarly, for this bit here, we've got this little triangle at the top, but we could still find the average height here, times that by the distance, or we could find the area of this triangle here, and then find the area of this section here. To find that total area, we could do the same thing for this triangle. Need to find this area. That's all nice and easy. Then the next bit, again, is constant. This bit here is constant. All of those easily findable areas and therefore easy to find the work done over that distance of motion. After we get past this though, we move on to this smooth, continuous changing shape here. We can no longer just break our graph down to simple squares, rectangles, and triangles that we know how to calculate the area for. Luckily, this is still going to work the same way. The area is still what's important. You could still imagine similar to this if you zoomed in extraordinarily far on, say, a section like this. At the limit, that's going to become basically flat, and you could find the area of that section. And then you could apply the similar logic to this next part here and go down, find that area. And if you take this distance here and have that go to 0 for these blocks, then the area you find will be an accurate representation of the total area under this graph. Those of you that are doing advanced mathematics will recognize this kind of idea for integration. If we had the formula for this force path I've drawn here, we could integrate that to find the area under this graph. However, in Year 12 physics, you're not expected to know how to do that. You don't have to take physics with maths, and so therefore you won't be required to do any integration to solve any of these problems. Instead, what you'll have to do is count up the area under the square, approximating it using boxes on graph paper. So you can see what an example problem might look like with the graph overlaid over the top of it. All you'd have to do now would be to count these boxes, see how many there are. I make it somewhere between 19.5 and 20 for this exact example. Once you have how many boxes there are in your image, you just have to work out how much each box is worth. In this case, remember, the reason we're looking for the area under the graph is because it relates to the work being applied to a block that undergoes these forces. So we'd have to work out how much energy, how much work is each box worth, and then therefore how much work is being done in total. Next week, we'll look at a specific example involving a satellite orbiting the Earth, which is a situation where this comes up a lot, and we'll have an explicit look at how this idea would work in practice.